Now let's look at the central limit theorem for the p-hat distribution. And so what the central limit theorem essentially says is that if you have that n times p is greater than or equal to 10 and n times q is greater than or equal to 10, then the distribution of p-hat is approximately normal. And so what this means is if you were to take your p-hats from all of your samples and you were to summarize them in a sampling distribution for p-hat, the larger the sample size, the more normal your sampling distribution is going to be. And so we usually just say that as long as your sample size times your proportion is greater than 10, that sample size is large enough for it to be approximately normal and for us to be able to use all of the properties that go along with the normal distribution. In this example, we're told that P is equal to 0.27, or 27% of all Americans prefer chocolate ice cream. And so we're going to take a sample of 100 people. And so this first question, what can we say about the p-hat distribution? It's essentially asking us if the p-hat distribution is approximately normal or not. And so to check this, we just need to make sure that the central limit theorem is satisfied. So I need to make sure that n times p is greater than 10 and that n times q is greater than or equal to 10. And so here we can calculate q real quick. It's 1 minus p, and so we're getting that q is equal to 0.73. So n times p, so 100 times 0.27, that's going to give us 27, which is definitely greater than or equal to 10. And then n times q is 100 times 0.73, which is 73. And again, this is definitely greater than or equal to 10. And so we can say by the central limit theorem, the p-hat distribution is approximately normal. What this means now is that we can use the properties of the normal curve to find probabilities related to our problem here. So for instance, if I scroll down to part C of this example, it asks the probability that the sample proportion is greater than 0.3. And so now we can use the normal curve to find that probability. But first we need to find the mean and the standard deviation of the distribution. The mean and standard deviation of this distribution is mu sub p hat, so that's the mean. And remember, this is just equal to p. In this case, p is 0.27. And then sigma sub p hat, which is the standard deviation or the standard error, is the square root of p times q divided by n. And so here we're getting 0.27 times 0.73 divided by 100. And this gives you 0.0444. So now I can combine parts A and B and actually draw out the curve for this p-hat distribution. And so I know the mean is 0.27. And the standard deviation, I'm going to say that this is approximately 0.004. I'm going to round it a little bit. And I know that one standard deviation away from the mean gives me a value of 0.314. 2 standard deviations away in the positive direction gives me 0.358. And so here's the completed normal curve for this p-hat distribution. So if we start working on part C, the very first thing we should do is rewrite this in probability notation. And so we're going to have the probability that p-hat is greater than 0.3. And so if you look at the normal curve, you notice that none of these values are exactly 0.3, which means I can't use the empirical rule. And so instead, you can either use the standard normal table, Or you can use, if you have a TI 83 or 84, you can use the normal CDF function. And so the way the normal CDF function works is the very first number that you put in is the minimum value that you want to see, right? So since I want everything greater than 0.3, if I draw that on my curve, I want everything greater than this value right here. So I want to find the area under the curve to the right of 0.3, which means 0.3 is the smallest number I want to see. And since I essentially want every single value greater than 0.3, I don't have a stopping point. And so I'm going to use a ridiculously large number as my stopping point. Because notice at some point this normal curve is actually the probability under the curve is going to be 0, or the area under the curve is actually going to be 0 after a certain point. And so if I put a crazy large number, like 100,000, then I'm guaranteed to be getting everything greater than 0.3. And remember, when you're talking about a p-hat distribution, these values on this axis all represent percentages or proportions. And so to put a value of 100,000 is essentially saying that this is 100,000 times 100%, right? And so this is a ridiculous value to put, but it guarantees that we'll get the right answer. Now the next two things that you enter when you use this normal CDF function is the mean and standard deviation of the distribution that you're looking at. And so we've already found our mean and standard deviation. So here you have 0.27 for the mean, and then the standard deviation is 0.044. So the first value we put in was the minimum value we wanted to see. The second value is the maximum. The third is your mean, so mu sub p hat in this case. And then the last is the standard deviation. And this is strictly if you're using the normal CDF function on a TI calculator. If you're using a Casio, I believe the standard deviation and the mean switch, but this is strictly if you're using a Casio. So after putting this into our calculator, we get a value or a probability of 0.2477. If you don't have a calculator that has the normal CDF function, then you can use this applet instead, and so I'll provide the link for this. But notice it's calculating areas under the standard normal curve, so the mean for this normal curve is 0, the standard deviation is 1. And so this is telling us the area greater than 1, so the area under the curve for z greater than 1 is 0.1587. So this is also the probability that you're going to get a z-score greater than 1. And so notice over here, there's a few things you can change. You can change the mean of this normal curve, the standard deviation of the curve. And then if you click this two-tail, what this does, and so if you leave it clicked right now, then what this does is if you drag it right now, then it moves both lines or both dots, right? So both z-scores, the positive and the negative one. And so this is if you want to find kind of combined areas, right? Then I could say the probability that it's both greater than 1.57 and less than negative 1.57 is this value times 2 because it's showing up twice, right? Or I could just add these. But if you unclick two-tail, then it just lets you move one line at a time. And so for our purposes for this example, I'm going to change the mean to the mean that we found, so 0.27. And then the standard deviation that we found was 0.044. And so now down here, this curve looks a lot like the one that I drew out, except they rounded it to 2 decimal places. So to find the probability that p hat is greater than 0.3, I can just drag this until this value says 0.3. And then this represents the probability that I'm going to get a value greater than 0.3, which also represents the area under the curve from 0.3 till the end of the curve. And notice this is the same exact probability that we found when I used the normal CDF function.